Welcome to the online training Introduction to Verilog. My name is Uriri and I will be your presenter for today. Here is today's agenda. We will begin the class with an overview of Verilog HDL, including the language history and commonly used terminology. Next, we will look at the structure of a Verilog HDL model and discuss general syntax rules for the language. We will then look at the components of a Verilog HDL model. This includes a discussion of ports, data types, assignments, and operators. Next, we will learn about behavioral modeling in Verilog HDL. We will learn when and how to use both continuous assignments and procedural blocks. Finally, we will talk about tasks and functions. Let's talk about Verilog Basics overview. What is Verilog? Verilog is an IEEE standard hardware description language, a text-based language used to describe circuits that will eventually be implemented in hardware. Verilog, like its competition VHDL, can be used to model hardware for the purpose of both simulation and synthesis. Here's a brief history of Verilog. It was originally created by Gateway Design Automation, which was purchased by Cadence. In 1995, it was adopted by IEEE as a standard. In 2001, a revised version of the language was introduced, and in 2005, IEEE accepted a new revision for the standard, which is in use today. Throughout this presentation and other literature regarding Verilog, you encounter many common terms. We will define some of those here. HDL, which stands for Hardware Description Language and is used to model hardware. When you use HDL, there are two ways you can model your circuit: behavioral modeling and structural modeling. We'll explore these in the next two slides. In behavioral modeling, you're describing the functionality of the circuit and not the structure of the circuit. The output behavior is described in relationship to the inputs. Here is an example of behavioral HDL code where a shift operation is being described. This type of modeling relies on the synthesis engine to create the correct circuits that match the behavior described. In the structural approach, both functionality and structure of the circuit are specified. The engineer writing the HDL calls out particular hardware elements and wires them together. Hardware element can be as simple as an AND or an OR gate, or could be a module that represents another layer of abstraction. In a typical modern design, you will find elements of both structural and behavioral models. RTL stands for Register Transfer Level. It's a common term that describes a style of behavioral modeling that defines input-output relationships in terms of data flow operations inside your hardware model. RTL constructs are synthesizable. Synthesis refers to both the translation and optimization of HDL code into a circuit of a particular technology. For example, lookup tables and flip-flops of FPGAs. RTL synthesis simply refers to the translation of an RTL model. This slide illustrates the process of RTL synthesis. In the first step, the synthesis engine translates your original code into hardware using architectural elements of your particular target device. It then goes through an optimization phase to ensure you have the optimal implementation of your circuit description. In this particular example, a case statement is implemented inside an always block, which typically infers a multiplexer. We will see more about these types of constructs later on in this presentation. The Verilog model you write can be sent through two different flow, synthesis or simulation. In the synthesis flow, the synthesis compiler, for example, Altera's native synthesis engine, will use the technology available in the target device library to translate and optimize your Verilog model into a technology-specific netlist that can be used for timing analysis or placed and routed into a specific device. In the simulation flow, the simulation compiler will simulate your Verilog model with stimulus provided either by a Verilog test bench or through test vectors. Most synthesis tools can also write out a post-synthesis Verilog file so that a designer can check the synthesis results before performing placement and routing. In this case, the output Verilog file from the synthesis tool can replace the original Verilog files in the simulator. The same test bench and test vectors can be used for this verification. Additional simulation model files may be required depending on the synthesis tool. These can be provided by the synthesis vendor or generated by the synthesis tool along with the post-synthesis model. Let's move on to section 2, model structure. We just completed an overview of Verilog HDL, its history and its uses. We will now discuss the basic syntax and structure used in Verilog HDL. Verilog HDL is case sensitive and all keywords are lowercase. Like C, Verilog HDL statements end with a semicolon. Single line comments begin with // while /* is used to begin a multi-line comment and // is used to end a multi-line comment. Verilog HDL is white space insensitive, which aids in readability. A Verilog HDL model is encapsulated by keywords model and end model, and it is also comprised of several main parts. First is the port list, which is specified with the model declaration. Next, the ports are defined. Then, variables and nets to be used in the model are declared in the data type declarations. After that comes the code that defines the circuit functionality. And finally, if applicable, timing specifications are made for simulation environments. We will examine the various parts of a Verilog model throughout this training. Verilog HDL is case sensitive and all keywords are lowercase. Like C, Verilog HDL statements end with a semicolon. Single line comments begin with // while /* is used to begin a multi-line comment and // is used to end a multi-line comment. Verilog HDL is white space insensitive, which aids in readability. A Verilog HDL model is encapsulated by keywords model and end model, and it is also comprised of several main parts. First is the port list, which is specified with the model declaration. Next, the ports are defined. Then, variables and nets to be used in the model are declared in the data type declarations. After that comes the code that defines the circuit functionality. And finally, if applicable, timing specifications are made for simulation environments. We will examine the various parts of a Verilog model throughout this training. This is Verilog HDL code for a model which produces a multiplier accumulator block shown on the right. At the top, the mult_arc model is declared along with a list of the input and output ports. The orange section is the port and data type declaration for all the variables and ports that will be used in this module. The green portion of the code is a continuous assign statement that will be synthesized into a combinatorial adder. The pink section is the code for the sequential register. Finally, the blue section instantiates another module that describes the multiplier. We will be going through each of the four major sections that comprise a Verilog HDL module throughout the class. So don't worry if you do not understand the code right now. By the end of the class, you will know exactly what this code is doing and why. A module begins with the keyword module, followed by the name of the module. The first sections of a Verilog HDL module is the port list. The port list contains all of the inputs, outputs, and bidirectional connections to a module. The port list is in parentheses immediately following the module name. After the port list comes the port declaration section. This section associates each of the ports with a port type. There are three port types: input, output, and in-out for bidirectional ports. The structure for the port declaration section is the port type, followed by the port name. Buses have a square brackets following the port type with the bus size inside. In this example, in A and in B are 8-bit inputs. CLK and ACLR are 1-bit input, while out is a 16-bit output bus. A module begins with the keyword module, followed by the name of the module. The first sections of a Verilog HDL module is the port list. The port list contains all of the inputs, outputs, and bidirectional connections to a module. The port list is in parentheses immediately following the module name. After the port list comes the port declaration section. This section associates each of the ports with a port type. There are three port types: input, output, and in-out for bidirectional ports. The structure for the port declaration section is the port type, followed by the port name. Buses have a square brackets following the port type with the bus size inside. In this example, in A and in B are 8-bit inputs. CLK and ACLR are 1-bit input, while out is a 16-bit output bus. With Verilog 2001 standard, you have the option of declaring port list and port type together with the module declaration. Here we see the same declaration as the previous slide, but in a more concise Verilog 2001 format. After the port declaration section comes the data type declaration section. There are two fundamental types of data in Verilog HDL: net and variable data types. Nets represent physical interconnects between processes or functional blocks. They need to be driven continuously and do not store value. Variable data types are used to temporarily store data. They are similar to variables in other languages. Variable data types may be synthesized into hardware flip-flops or registers or combinatorial nodes depending on usage. Here are four most common net data types supported by synthesis. A wire and a trie both represent a node. The trie-net type is used to represent a tri-state node. Wires and tries are used for interconnects. Supply 0 and supply 1 represent a constant logic value. They are used to hardcode logic 0 and logic 1. In the examples given, out is of type wire and bus size 8, while enable is a tri-state node. Net needs to be driven all the time. For example, using the continuous assign statement. Variable data types represent temporary storage. They can be of type reg, integer, real, time, and real time. Reg type is a variable of any bit size. Adding the signed keyword will invoke signed implementation. Reg type does not necessarily refer to a physical register. Actual implementation will depend on usage. Integer represents 32-bit signed variables. Real, time, and real time are there for simulation purposes only. They do not have synthesis support. Variable data types need to be assigned inside a procedure, a task, or a function. We will see later what these mean. They cannot be driven using the continuous assignment statement assign. With the reg data type, bus declarations can be made the same way wires can. Once a module is declared, it may be instantiated at a higher level module by using the syntax here. First is a lower level component name. This is the name of the component that you have declared. If you wish to express a time delay through the component, you may use the optional #delay construct. This is used in simulation only and not during synthesis. After that, specify an instance name. This is the unique name applied to the component instance. Finally, specify a list of signals you wish to connect to the inputs and outputs of the lower level component. You must follow certain rules regarding signal types that I will present later. By instantiating modules, you can create designs with multiple levels hierarchy to achieve easier maintainability. Modern designs typically have many layers of hierarchy. When connecting signals to lower-level module ports, there are two ways to define the connections: by ordered list and by name. In the example here given on the right, I am instantiating two instances of the half adder module to form a full adder. For the first instance, U1, I've instantiated using the ordered list method. Here, I'm connecting higher level signals to the half adder module's ports by listing the port list in the same order as the port list in the lower level module declaration. Order of the port connections does matter, so you should only use this method for modules with few ports. For the second instance, U2, I am instantiating using connections by name method. Here, I have specifically stated which wires connect to which port. Here, the order of the port connection does not matter, and I may leave out certain ports that I do not wish to connect. This is the recommended method because it's much easier to see how the connections are made without diving into the declaration of the lower level module. Connections into and out of modules must obey certain rules. Ports of a module and the connections to a module can only be declared of certain data type. When declaring a module, signals of the variable type cannot be used as input or in-out ports, while the net data type can be used in all situations. Implicitly, input and outputs default to wire if no type is specified. When connecting a signal to a lower level module's ports, variables cannot be connected to outputs or in-outs of the module, while the net data type can be used in all situations. Parameters can be used to associate a value to a symbolic name. This is done using the keyword parameter. Thus, you can base construct information like size and settings on the symbolic names to make the code readable and meaningful. Parameters can be overwritten during compilation from a module instantiating the module containing the parameters. The exception to these is by defining a parameter as a local parameter using the keyword localParam. By defining a parameter as a local parameter, this means that it cannot be overwritten at compile time. All types of parameters must resolve to a constant value at compile time and cannot be changed during module execution. Parameters can be floating point, referred to as a real parameter. In the example here, I'm declaring size and outsize as parameters, resolving to 8 and 16 respectively. They are then referred to when declaring variables data A, data B, and out. With Verilog 2001, you may declare your variable along with the module declaration. Numbers can be assigned to variables in two ways. They can be sized or unsized. If you don't specify a size or format for a number, they will default to 32-bit decimal number. The format of a number is size, tick, letter, or letters indicating format, and then the actual number itself. If you specify a sized number, the width of the number in bits must be specified before the tick. Base format can be D, H, B, or O, as indicated in the slide. You may also add S to indicate a signed or 2's complement representation of the number. So in the example, 16 tick SHFA is equivalent to minus 16 tick H06. To specify a negative number, put a minus sign before the size. Placing the minus sign anywhere else will result in an error. There are a few special characters that apply to numbers. First, you can use an underscore to improve readability. The underscore will be ignored by Verilog HDL. An X represents an unknown value and a Z represents a high impedance value. If the most significant bit is 0, X, or Z, the number is extended to fill the most significant bits with 0, X, or Z, respectively. If the most significant bit is 1, number is extended to fill the most significant bits with 0. In terms of arithmetic operators, Verilog defines add, subtract, multiply, divide, modulus, and exponent. Some synthesis tools may not support divide or exponent. Others support them only if the second operand is a constant. The operators treat input vectors as a whole number, so if z or x values appear in part of the operands, the result will be unknown. A in plus d in will give unknown. Also, if result vector is the same size as the operands, then carry will be lost. It is important to note that the exponent may not be fully supported by your synthesis tool. Verilog HDL's bitwise operators can be unary or binary, and they include inversion, and, or, exclusive or, and exclusive nor. These operators operate on each bit of the operands. If the operands are different sizes, the smaller operand is left extended, and the result is the size of the largest operand. Reduction operators are unary operations that reduce a vector to a single bit. Verilog supports AND, NAND, OR, NOR, exclusive OR, and exclusive NOR reduction operators. Each of these operators results in a single bit result. Even though x and z are unknown values, the result may still be known. For example, if you AND a vector with a 0 in it, the result will be 0 regardless of whether an x or z bit is present. AND b in equals 0. Relational operators are used to compare operands. They return a single value. Here are the relational operators supported by Verilog HDL: greater than, less than, great than or equal to, and less than or equal to. The result is either true or false, represented by 1 or 0. If either operand contains a z or an x, the result will be unknown. Like relational operators, equality operators are also used to compare values. They return one bit true or false value. Verilog HDL supports four equality operators: equality, inequality, case equality, and case inequality. There is often confusion between equality and case equality. The equality operators only support the known values 1 and 0. So if there are x or z's in your operand, results will be unknown. Case equality supports comparison of all values. X and z's are considered distinct values and must be matched exactly. Case equality is often used in simulation environments. Logical operators can be unary or binary. Verilog HDL supports not true, logical and logical or. These operators are typically used in if and while statements. These operators return a one-bit true or false result. Appearance z or x bits in the operands will cause an unknown result. Shift right and shift left operators are supported. These operators will shift a vector left or right by a specified number of bits. For left shifts, vacated positions are filled with zeros and the shifted bits are lost. For right shifts, logical and arithmetic unsigned shifts will be filled with zeros, while arithmetic signed shifts will be filled with the signed bit value. Here are the three miscellaneous operators also popular in Verilog. The conditional operator acts like a compressed if-then statement. The syntax is a condition followed by a question mark, followed by the expression to evaluate if the condition is true. That is followed by a colon and the expression to evaluate if the condition is false. Concatenate operator combines two or more vectors to form one larger vector. The replicate operator takes one vector and replicates a specified number of times. When you are using multiple operators together, it is recommended to use parentheses to group operations for clear understanding and readability. If parentheses do not exist, here you can see the priority of the operators as defined by Verilog. Unary operators will have the highest priority. Now let's move on to section 3, making assignments. In Verilog, there are two ways to make assignments: with continuous assignment statements and with procedural assignment statements. A continuous assignment is used to represent combinatorial logic. The left-hand side must be a net data type. Remember that net data type includes wire and try. Continuous assignments are always active. This means that any change to one of the values on the right-hand side of the assignment results in the left-hand side of the assignment being updated. Continuous assignments can be made implicitly when the net is declared, as in the example at the top right. Or you may choose to use the assign keyword to make the continuous assignment later in the code. In a simulation environment, delays can be assigned to the assignment to model actual gates. In the example given, assign #5 adder out equals mult out plus out. If mult underscore out or out changes, then adder underscore out will be updated with appropriate changes 5 time units later. Procedural assignments are made inside procedural assignment blocks. There are two types of procedural assignment blocks: initial block and always block. Initial blocks are typically used to initialize behavioral statements for simulation. Always block, as indicated by its name, is always executing in a looping fashion. They are used to describe circuit functionality. A typical design will typically include many initial and always processes. The processes all run in parallel, but the statements within a process are sequential. Each process begins at time 0 in a simulation. Initial blocks are typically used in simulation for the purposes of initialization or monitoring, although some constructs may also be supported in synthesis. For example, you may choose to use the initial block to specify initial RAM content. Initial blocks consist of behavioral statements, and these behavioral statements inside the block execute sequentially, so order does matter. The block executes only once, starting at time 0. However, depending on the statements inside, it may take infinite amount of time to complete executing the statements inside. Like initial blocks, always blocks also consist of behavioral statements. Always blocks are used to model a process that repeats continuously in a circuit. Like an initial block, always blocks start at time 0, but always blocks execute continuously in a looping manner. If you have multiple always blocks, as is probably the case, all the blocks will execute concurrently. However, statements within an always block execute sequentially, so order does matter. If there is more than one statement within a procedural block, either initial or always, the statements must be grouped together using the keywords begin and end. Here is an example of an always block and an initial block. The first initial block initializes the clock signal to 0 at time 0. The always block will toggle the clock signal. A pound sign followed by a number produces delay. In this example, period is set by a parameter. The always statement toggles the value of the clock every 25 times units. The second initial block causes the simulation to stop after 100 time units. Here is an example of an always block and an initial block. The first initial block initializes the clock signal to 0 at time 0. The always block will toggle the clock signal. A pound sign followed by a number produces delay. In this example, period is set by a parameter. The always statement toggles the value of the clock every 25 times units. The second initial block causes the simulation to stop after 100 time units. There are two types of assignments within an always or initial procedural: blocking and non-blocking. The left-hand side of a procedural assignment must be a variable data type, either reg, integer, real, or time variables. The right-hand side of the assignment can be any valid expression or signal. The value placed on the variable will remain until another procedural assignment updates it. Blocking assignments are executed in the order that they are specified in a sequential block, meaning statements after a blocking assignment won't be evaluated until the blocking assignment has finished executing. Non-blocking assignments, as the name suggests, do not block the execution of subsequent statements. The compiler schedules non-blocking assignments to be executed at the end of the time step, and then moves on to the next statement before actually executing the non-blocking assignment. Here is an example of blocking versus a non-blocking assignment. You can see that in the blocking case on the left, A is assigned the value of B after 5 steps. C gets the value of A after another 10 time steps. Because the statements are blocking, the assignment of C does not get evaluated until the assignment of A finishes executing. So at simulation time step 5, A gets the value of B, and at time step 15, C gets the new value of A, which is the same as the value of B. In the non-blocking example on the right, the compiler schedules the assignment of A at time step 5, but then moves on to the next statement, which schedules the assignment of C at time step 10. In this case, A gets the value of B at time step 5, but C gets the value old A at time step 10. This is because at the time the compiler is evaluating this statement, the first statement hasn't executed yet. Here's a great illustration of how blocking and non-blocking assignments are synthesized. On top in the blue section, we have x equal next underscore x because there's only one statement inside both the blocking structure on the left and the non-blocking structure on the right. They both infer the same logic, and the logic synthesizes into a single flip-flop. Looking at the bottom green section, there are now two statements with an intermediate variable x. We can see now how different behaviors can be achieved through the use of blocking versus non-blocking assignments. This time, the blocking assignment resulted in a single flip-flop because the first x assignment is blocking the y assignment. So the value of next underscore x is transferred to y through x during the same clock edge, so only one flip-flop is inferred. In the non-blocking assignment, because the first statement is non-blocking, y assignment is evaluated before the x assignment is executed. So y gets the value of x prior to the clock edge, and so it takes 2 clock cycles for the value of next underscore x to get to y. Because of this, 2 registers are inferred. A good rule of thumb to follow is always use blocking operators for combinatorial logic and non-blocking operator for sequential logic. These will avoid confusion and improve the readability of your code. Let's talk about writing RTL synthesizable processes. The always block can be defined with an associated sensitivity list. A sensitivity list controls the execution of an always block. The sensitivity list follows the keyword always and begins with the @ symbol. An always block will only execute after a change in any signal in the sensitivity list. Sensitivity lists can be further controlled by adding the keywords pos edge or neg edge, indicating that only positive or negative edge transitions will trigger the always block. We can use the sensitivity list to infer either combinatorial processes or clocked processes. A combinatorial process is sensitive to all inputs used in the combinatorial logic. You may choose to use asterisks as a shorthand for all signals. A clocked process, on the other hand, is sensitive to only a clock and an asynchronous control signals. We will now talk about 3 types of behavioral statements you can use inside a procedural block: if-else, case, and loop statements. If-else statements are evaluated in order from top to bottom. This results in prioritization. The first condition that is true results in the corresponding sequence of statements to be executed. Case statements evaluate all conditions at once. This results in a circuit with no prioritization. All possible conditions must be evaluated when using a case statement. The default clause covers all cases not specifically stated. Loop statements are used for repetitive operations. These statements will be expanded in hardware. Here is an example of if-else statement. The statement begins with the keyword if, followed by a condition, and then the sequence of statements to execute if the condition is true. The else clause, if it exists, will be executed when the condition is false. You can see that if statement synthesizes to 2 input muxes. You can also see that multiple if statements result in multiple muxes, resulting in prioritization. If you do not need prioritization in your circuit, a case statement will be more efficient. In a case statement, all conditions are checked against an expression. This results in one mux with multiple inputs. Conditions are evaluated in the order they are written and does not need to be unique. The format for a case statement is the keyword case, followed by the expressions to be checked. Then comes a list of conditions followed by their corresponding sequence of statements. You may choose to use the default condition as a catch-all for all other unspecified conditions. Finally, it ends with end case. By default, case statement will treat x's and z's as logic values and compare them to x's and z's in the list of conditions. Don't cares are denoted by the question mark characters. However, there are two additional forms of case statements that won't follow this default behavior. The case z statement treats all z values either in the expression or the conditions as don't cares. The case x statement treats all x and z values as don't cares instead of logic values. Loops are used for repetitive tasks. In a forever loop, the loop continuously executes. This creates an infinite loop. In a forever loop, it is important to make sure that time advances or else simulation will break. In this example, time advances 25 time steps during each iteration of the loop. A forever loop is not synthesizable. A repeat loop repeats a section of code a specified number of times. In this example, the repeat loop is executed 8 times. Another example of a Verilog loop is the while loop. A while loop executes if the associated expression is true. In this example, while count is less than 101, the loop will execute. This while loop counts from 0 to 100 and exits when count is equal to 101. Another common type of loop is the for loop. A for loop executes as long as the expression provided is true. In this example, I is assigned to 4 at the start of the execution of a loop and is then incremented by 1 before each pass through the loop until I is greater than 7. This loop results in a 4-bit left shift. In C, you can alter the count variable within the loop, but in synthesizable Verilog, you cannot alter the count variable within the for loop. In hardware, loops are unrolled. It is important to consider which function resides in the for loops. If the above example included a multiplier inside the for loop, 4 multipliers would be implemented in hardware. The way we code the sensitivity list will result in a control signal being synchronous or asynchronous. We need to include asynchronous signals in the sensitivity list of the always block. Here are two examples of D flip-flops. The example on the left creates a flip-flop with a synchronous preset and clear. You can see that the process is only sensitive to the positive edge of the clock signal. Once the clock goes high, the clear and preset signal are checked in the if statement. If neither preset nor clear are set, then Q gets D. The code on the right also creates a D flip-flop, but implements an asynchronous clear. The sensitivity list contains both the clock signal and the asynchronous clear signal. Within the process, an if statement checks to see if the clear signal is high. This slide illustrates how to code a clock enable. The example here creates a flip-flop with a clock enable signal. On the positive edge of the clock, the process checks the enable signal. If the enable signal is high, then Q gets D. If the enable signal is low, nothing happens. Q will keep its previous value. This counter example pulls a number of concepts together. The counter has an asynchronous clear signal. When the process is entered, the if statement checks the asynchronous clear signal. If that signal is high, the counter is reset, otherwise, we move to the else clause. The case statement within the else clause checks the func control signal. This 2-bit signal controls the 4 functions implemented in this counter: load, count, up, count, down, and no change. Notice that the last test for the case binary 11 is not included. Verilog does not require it to be specified. We could have specified that Q gets Q when 11 is encountered. This is completely redundant, as this behavior is implied by the functionality of the variable Q. A variable will always retain its current value until it is driven with a new value. This counter example pulls a number of concepts together. The counter has an asynchronous clear signal. When the process is entered, the if statement checks the asynchronous clear signal. If that signal is high, the counter is reset, otherwise, we move to the else clause. The case statement within the else clause checks the func control signal. This 2-bit signal controls the 4 functions implemented in this counter: load, count, up, count, down, and no change. Notice that the last test for the case binary 11 is not included. Verilog does not require it to be specified. We could have specified that Q gets Q when 11 is encountered. This is completely redundant, as this behavior is implied by the functionality of the variable Q. A variable will always retain its current value until it is driven with a new value. Verilog HDL has 2 types of subprograms: functions and tasks. They both must be defined within a module. A function returns a value based on its inputs. Functions typically produces combinatorial logic and are used in expressions. In this example, we are continuously assigning mult_out to the output of the function mult with inputs in A and in B. Tasks are similar to procedures in other programming languages. Tasks can be either combinatorial or registered. A task is invoked as a statement rather than as an expression. Tasks and functions are useful for repetitive code within a module. They improve the readability of your code. Here is a function defining a multiplier. You can see that this is a standard multiplier with 2 8-bit inputs and a 16-bit result. Notice the keywords function and end function, defining this piece of code as a function. Also notice that mult gets R at the end of the function. Functions always return the value assigned to the name of the function, so the last operation in a function often assigns a value to the name of the function. Here is a function defining a multiplier. You can see that this is a standard multiplier with 2 8-bit inputs and a 16-bit result. Notice the keywords function and end function, defining this piece of code as a function. Also notice that mult gets R at the end of the function. Functions always return the value assigned to the name of the function, so the last operation in a function often assigns a value to the name of the function. Here's an example of a function invocation. This is also our last look at the multiplier accumulator example that we have been working with throughout the class. Mult_out is being assigned the value of the mult function. One advantage of using a function is to make your code more readable. In this case, the details of the multiplier are not shown in the mult_arc module. Here's an example of a function invocation. This is also our last look at the multiplier accumulator example that we have been working with throughout the class. Mult_out is being assigned the value of the mult function. One advantage of using a function is to make your code more readable. In this case, the details of the multiplier are not shown in the mult_arc module. Here is a complete task example. This module contains a task called add with 2 inputs and 1 output port. In the initial block, I am calling the add task with 1 and 0 as inputs and connecting the C output of the add task to my reg variable P. The last part of the initial block simply uses the system call display to show the value of add, which will be 1. Here is a complete task example. This module contains a task called add with 2 inputs and 1 output port. In the initial block, I am calling the add task with 1 and 0 as inputs and connecting the C output of the add task to my reg variable P. The last part of the initial block simply uses the system call display to show the value of add, which will be 1. There are a number of differences between functions and tasks. First, functions can only call other functions, while tasks can call either functions or tasks. Functions are combinatorial logic, so they cannot contain any delay, event, or timing control statements. Tasks do not have these restrictions. Functions must have at least one input. Tasks are not required to have any input, but may. Functions must return exactly one argument. Tasks can return 0 or more arguments using output arguments. Functions cannot have in-out or output arguments. This takes us to the end of this online training. We've talked about the basic structure of a Verilog model and discussed many components of a Verilog model. For additional reference material, check out the Advanced Synthesis Cookbook or the Quartus Prime Standard Handbook Volume 1, Design and Synthesis. If you would like to receive additional Verilog HDL training, you may follow the links to sign up for either the Intro to Verilog or Advanced Verilog instructor-led classes from Altera. The Altera training team is always looking to improve our material. To do this, a survey will be emailed to your registration email address. We'll welcome any feedback you may have. Thank you very much for attending this training.